Hello and welcome to a project using SonicPi 3 in conjunction with TouchOSC, which is running on my iPad. You can see an image of the iPad at the bottom of the screen here, and at the top we have SonicPi 3.01, which is running on my MacBook Pro and is running a little program in which I'm exploring the interaction between two tone generators running on SonicPi. For a long time I've been interested in looking at long notes in SonicPi. That's ones where the note is initiating just runs more or less continuously, although in this case I put a limit of 100 seconds on it. And by using SonicPi, using TouchOSC, I can actually have two oscillators running and just explore how they interact as their pitches or frequencies are altered. And this is where a program like TouchOSC is very, very useful for SonicPi. It can interact with it in two ways, either by sending MIDI information to SonicPi, or in this case, sending OSC messages to SonicPi. And this gives a great deal of versatility and greatly extends the usefulness of SonicPi by being able to control it in this way. It in fact has various live loops running here. The whole lot is inside an FX reverb function, and the two main live loops, the first one here controls note number 1, and it waits for a signal to come via an OSC message which is addressed to OSC note gen note 1, and that sends the value of one of these sliders. In fact, the left-hand slider here on the TouchOSC screen, and that varies between -1 and +1 for its output, 0 when it's in the middle, and so at the moment it's going to give you an output of about 0.8, and that is read into the variable n1 here, and that is going to be set or stored so that we can use it subsequently in another live loop. Also, because I want these notes to sound continuously, when I start a note, which I do down here, with a standard play function, you'll see it's going to play and it's going to get the value of n1, which we stored up here, and it's going to multiply it by r, which is going to be a range factor, which is set by the switch on the TouchOSC screen here, and is either going to have a value 0.1, 1, 4, 7 or 12. These are in fact in semitones, and so at the moment on the screen it's set to 1, so R would have a value of 1, and it's also going to add the result here to the starting pitch, which is 72. So in this particular case, as the slider goes up and down, it would vary the pitch of this note in MIDI values between 71 and 73, with 72 being the value when it's in the middle. You can see that the note has a very long release time of 100, and it has a short attack time. This is just to try and reduce the clicks as the note starts. Now, the reason that I have K equal to the note here is to maintain or keep a reference to that note, which is stored here into the variable kv1. And when we change the pitch of the note, what I do is I get that value kv1, and the first thing I do is to kill the note which is already sounding. And we're going to control K, that's the pointer to the note. We're going to set its amplitude to 0 with a very quick rapid fade, and then we're going to kill it or stop the note from sounding. And then immediately we're going to restart the note with the new value of n1, which has been set in as the loop goes round here when it receives a change signal from the slider. This is just going to get the value of the range function r, which is set in another loop as this switch here is going to be changed. The second slider is going to control the second live loop here, and it's exactly identical to the first one, except that the variable is going to store the reference to this note sounding in kv2, and obviously the pitch is going to be given by the value N2, which depends on the second slider. Otherwise, it's identical to the first one. Then in the middle of the TouchOSC screen, we've got three buttons, one green, one red, and one yellow. The red button is going to stop all the sounding notes, and that's going to be controlled by this live loop here, kill note do, and that's going to stop the note from sounding, and we are going to receive that signal. It's going to check whether the button is actually depressed rather than just released, in which case the value it receives will be greater than 0, it'll actually be 1. It's then going to get the value stored for the currently sounding note 1, and it's going to kill that. It's going to get the note for the currently stored value KV2, and it's going to kill that note, so it's basically going to stop those notes from sounding. When the green button is pushed, we're going to be looking at live loop start note here, and that is going to get a message OSC note gen start generated when the green button is pushed. It'll check whether the button is pushed, that'll be a 1 if it is, and it's then going to simulate an input from the two sliders by sending an OSC message back to SonicPi as if it's coming from note gen note 1, and it's going to get the stored value of N1, the last value which was stored in this loop back here, and it's going to effectively therefore restart that note with that value, and it's going to do the same thing for the note 2 loop, and it's going to send to it the stored value for N2. So by pressing the red and the green buttons, we can switch the note on and off again. The final loop is controlling the well, in fact, there's two others. The first one, we'll come back to this get button function in a minute, but this one here is going to get the range value. And this switch that we have here, which if I touch it you can see is altering, is in fact what's called a multiple toggle switch. Only one of these settings can be active at once, and whichever one is active, it's going to send a message to SonicPi, and if you look on the right hand side of the screen here, you can see the OSC messages arriving. If I press the top one there, the message which it's sent is OSC note gen range 5/1, because that, counting from the bottom, is 1, 2, 3, 4, the fifth entry up. If I press the bottom one, the message is going to be sent to OSC note gen range 1. You can see 5-1 for that one, 1-1 for that one. There's the second one, which is 2-1, the third one, which is 3-1, the fourth one, which is 4-1. Now, so that we can get all of these in one live loop, rather than having a separate one to detect each one separately, I'm syncing this on OSC note gen range, and I'm putting a star, which is a wild card there, and that will then match either 1, 2, 3, 4, 5, or in fact 6, 7, 8, or 9 if they happen to be there as well. And therefore we know that one of the buttons has been pushed, but we don't know which one has been pushed. The next line is going to detect whether it's been pressed, because it doesn't want the signal sent when one of these is switched off to trigger things, only the one which is being switched on. And it's then going to work out which button it is, and that's where this little function up at the top comes. Now this is slightly naughty in that it uses a function in SonicPi which is not advertised, it's not public. That's because it's still a sort of trial function, and Sam hasn't added it to the full API yet, principally because it's a bit of a hairy thing to use, and it's not sort of, as he likes to say, 8 or 9 year old proof at the moment. It gives a pretty horrible output when you use it, and you can see that when I use it here, I'm having to do a bit of Ruby jiggery pokery here to extract the information I want from it. What the get event address does is that it returns a string containing lots of information about the event when this button is detected, and from that I'm extracting the full address, and I'm working out what the actual star was that caused this to be triggered. In other words, which of the buttons 1 to 5 was pushed. So that's all you really need to know about it. Don't worry too much about the specifics unless you want to get really into the code, in which case you could start by looking at what get event OSC note gen range *1 would return, and you'll see the sort of thing that you've got to deal with in order to extract this. But just leave that on one side. It just makes it a bit more efficient as a way to work out which button has been pushed. And that will be a number, in fact, in the range 1 to 5. Since we're going to set the range from a list here of these 5 values, we actually index that link from 0. So I subtract 1 from the range, from the R value, which is obtained here, to get the actual value which I store in range. And that can then be used where it is required in the 2 note loops, where it is extracted up here to, where are we? There we are, R get range. It extracts it so that it knows what to multiply the slider value by to get the note we actually want to hear. So that's probably the hardest bit of the program to follow. The last bit is another live loop, and this is used to reset the 2 sliders to the 0 position in the middle, and it does that by sending back to the TouchOSC screen here, OSC send to the remote IP. That's the address of the TouchOSC program, port 9000. That's what it's set up to listen to. If I just turn over here for a minute and you look there, you can see that its IP address is 192.168.1.240, and that it is listening for incoming information and port 9000. So that's where that has actually come from. If we go back to the screen there, and it's going to send to that, to the note 1 slider, the value 0, and to the note 2 value slider, the value 0. And so to keep things in sync, it's also going to set the stored note values for the slider positions for N1 to 0 and for N2 to note 0. So that's quite a lot of technical gumph about the program. Let's have a look at it in operation. The other thing that happens is when I start the program running, it's actually going to send some information to the TouchOSC just to initialize it. Here, for example, it's going to set the range switch, and it's also going to use the note gen reset loop down here that we've just been discussing to set the sliders back to their 0 position. So I'm now going to come up here and click on the start button, and if you look at the TouchOSC image at the bottom, you'll see that that's initialized. 3, 2, 1, go. And you can see that it's initialized the note values, the sliders to the 0 position. It's set the range to 12, and we're ready to go. So let's try moving one of the sliders up like this. And you can see that we can get a continuously sounding note. We can change the pitch of it. It goes in discrete little jumps there because I have set a time delay on the loop as it goes round, so that to try and reduce the crackling as much as possible, but it does give quite a reasonably smooth variation in pitch as we move up and down. And the notice I say, if we don't do anything, will continue to sound for about 2 minutes, 100 seconds, and it will then stop. You could make that 100 bigger if you want, but I thought that was a reasonable value to set for it. We can leave that running, and we can start the second one running at the same time. like that. Now we could also come up here and switch on the waveform, and you can see the two notes very nearly related there pitch-wise, giving that sort of pattern. If we put them both the same, we will get we can get beats between them. Let's just change the, first of all, we'll set these back to 0. If I press 0 slider, those go back. We need to update that, like that. And both notes are exactly the same now. Now, if we change the scale and update that again, we've now only got 1/10 of a semitone variation as the slider goes up to the top or down to the bottom. So let's move that slightly. And you can see and hear the very low beat frequency. Make it a bit bigger, a bit more rapid, a bit more. We'll go up with the other one. So it's a nice way to explore the beating function. One could do the Lissajous one as well, but it's not very interesting because the two sine waves are actually in phase with each other, so you just get a 45-degree line rather than a circle, which you get if they were out of phase with each other. So we can switch off and on the notes at any time. Remember, it actually kills the note and then restarts it with the current values for N1 and N2 when we do that. We can start one as soon as we change, of course, the slider. It would restart a note. We stop it. Not moving very far, of course, because we've got a very low range. Let's take the range up a bit. One of the other nice things you can do is this. If we set those an octave, 2 octaves apart, like that, change the range and update, we get that sort of effect. So, I hope that gives you a good introduction to the program. As you can see, it's just really an experimental thing to play around with some notes and different pitches and different ranges, but it does illustrate just the power of using something like TouchOSC to add external controls to SonicPi. You could do all this with a MIDI controller, maybe a hardware one with some knobs or slides on it as well. But I find TouchOSC particularly useful because you can actually design the layout exactly as you want. You simply choose graphical representations of whether you want sliders. I could have used rotary controls for these as well by choosing a different symbol when I design the layout using the TouchOSC editor, which comes with this. But it is just so versatile to actually do things like this, and you can have a lot of fun just playing around with all of this stuff and using SonicPi to generate the notes, but also to interact with the controller in a very simple way once you get the hang of how to use OSC messages. Perhaps just one final gotcha to mention for anybody who's going to try and do this themselves. You'll notice when I send a message from here to SonicPi, I sent /notegen/reset. But if we look down at the bottom at when we detect this in the reset sliders live loop, it's actually looking for the address /OSC/notegen/reset. Notice the /OSC at the front. And that's because, by design, SonicPi automatically inserts /OSC into the messages for all incoming OSC source messages, just as it will insert /MIDI if the source is from a MIDI controller. And that is so that in the cues log down here, you can very quickly see the source of any cues which are being generated, because that's essentially what this does. This is actually a cue which is generated. We're using a sync function to test for it in this live loop which continuously goes round. And so by having OSC at the beginning, we know it's an OSC message, whereas here, live loop get range, that's just an automatic cue set by the get range live loop as it starts. Well, this will happen automatically unless we turn it off. And so we can distinguish between internally generated cues from a live loop and externally generated ones from OSC messages. And you'll see also that the set and get functions are also logged in here. These actually generate changes of state in the time line, setting or getting information which can be stored there. So I hope you've enjoyed the video, and maybe you're inspired to have a go yourselves. Thanks for watching.